because you don't want to fail the joint. So always the objective of any structure is the joint should never fail. And the waste cost efficiency of the joint. Common joint methods, as he said, the bolted joint and adhesively bonded joints. Mostly it's the bolted joint which are common. Bonded joints are not very common. And we'll discuss the issues with various joints. Okay, bolted joints advantages. Widely applicable to assembly and joining of various structural elements. Use of conventional metalworking tools and techniques as opposed to adhesive bonding. Utility of repeated assembly and disassembly of fabrication, replacement or repair. Ease of joint inspection for quality. Assurance of structural reliability, no surface preparation required. Low risk, easy to repair, and is mature technology, bolted joints. So these are the advantages. However, there are disadvantages. When you drill the hole in a member for the fasteners, naturally you are reducing the area and creating some stress concentrations in the members. So that means your strength of the member, suppose you're joining two laminates, the laminate strength, which would have been higher if there were no holes, it would be reduced. So that means strength degradation of basic laminate due to holes. Increased weight, because it has a lower structural efficiency, and we will talk what is the structural efficiency of bolted joints. So that means if it has a lower structural efficiency, increased weight. And I'll show you one chart where I would say bolted joints, the maximum efficiency for composite bolted joint around 40 to 45% is possible. If you have aluminum to aluminum joints, fastened joints, you can go up to 70% efficiency. And bonded joints, you can achieve almost 70% efficiency, could be more. So that way, the bolted joints and composites, that's one of the disadvantages. The joint efficiency is low. And we'll discuss why so. Careful design required of joints due to uneven load distributions on fasteners compared to metal structures. That also we'll discuss. That when we are joining two members together, there are multiple fasteners. If you have 3 rows or 4 rows of fastener, not each fastener carries the same load in composites. In metals, I'll show you that at ultimate, because of ductility of the metal parts, the load distribution becomes more uniform compared to the composites. So in composite joints, some fasteners are heavily loaded, some are less loaded, and that reduces the efficiency of the joints. Increased cost due to increased number of operations, because you need a drilling operation, assembly, that increases the cost. Potential fastener corrosion resulting from contact with carbon. Now, I discussed during certification lecture the galvanic corrosion issue. When you are interfacing the carbon part with aluminum corrodes in presence of carbon. So in order to prevent that, you have to provide some kind of a barrier, which is usually glass ply between aluminum and carbon, to avoid the galvanic corrosion. It's labor intensive. It requires more man hours to drill the holes, put the fasteners, assemble it. It requires shimming leading to fit up stress. Sometimes when the two members are joined together, then they don't fit. So you require some kind of a shimming. And I'll talk about the shimming. Shimming is not a very good idea. They degrade the joint strength significantly, especially the fatigue. Expensive fastener. Fasteners are very expensive. Some of the fasteners, if you have to use like in-canal fastener, there's quite expensive fasteners. Lower structural efficiency compared to adhesive joint, which I discussed. Okay, now adhesive joints, advantages, reduce fastener count weight, there is no fastener, so that means reduced weight. Can join thin sheets compared to bolted joints? Bolted joint strap thickness is dictated by countersink depth of the fasteners, and we'll discuss that minimum thickness of a laminate, because of the countersinking, has to be, almost 1.5 times of the countersink depth. No pad-up required to accommodate holes, fasten joints. Aerodynamically smooth surface. Reduced parts for assembly. Reduced assembly time. This is all from bonded joint. Higher structural efficiency compared to bolted joint. We could achieve almost 70 to 80% efficiency. Possibly lower weight, no drilling of holes, and thus no stress concentration, and that increase the efficiency. However, there are disadvantages. And in fact, the disadvantages outweigh the advantages for the adhesive joint, so they are not that popular as the bolted joint. Highly process dependent, requires surface preparation for bonding. Bond line not inspectable for their quality. The biggest problem of the bonded joints is that you can't inspect the bond line strength. NDT will tell you whether there's a bond, but how good the bond is, that is not possible. So that means you are running the risk of the joint failures. And this is one of the biggest drawbacks of adhesive joints. Adhesive strength degradation due to moisture and temperature. This is another thing. Moisture peeps through the adhesive bond line, it will degrade it. Difficult to detect bond failure before complete failure or joint failure. You can't detect, you can't see bond line failure. Difficult to disassemble the assembly. Complicated field repairs. If the damage occurs in the field, difficult to repair, complicated. Complex tooling, because when you are processing the bonded joints, it requires complex tooling, and that becomes expensive. Curing of adhesive required, limited in application. Not everywhere you can have a bonded joint. Okay. Now here there are some examples of the type of the joints you might have, like a double shear, multi-row, double shear joint, single shear, multi fasteners, the tension load joint, like a T joint. This is a double. At this angle, this is a T. So trailing edge joints, single shear, double shear. Okay. Some various joint schematics, suppose side of body fairing. If you have side of body fuselage, then a skein going, the skein is spar cap, they're all together because finally they have to be joined to this. And this becomes very critical joint, in fact, because you are attaching the wing to the fuselage, and wing is highly loaded structure, so these joints become very critical. Then this is scheme I have shown earlier in my screen. Okay, now the type of you may have only 2 straps in a joint, or you may have a multiple straps, several, because what happens quite often in this structure, you may have a skin, you will have a spar, then you may have a joggle, D-nose, all together. There may be 5 or 6 members to be joined together, like this, what you have. And there are shims, sealant. So that way the joint design becomes difficult. Okay, what I had said, the difference between the metal joint straps and composite joints, when you're having, suppose you have these 4 fasteners and you're pulling the load from here, this reacted this way, and this is whether they are metallic strap or composite. Suppose metal straps, then what will happen? initially, when you start loading the joint, the material is not yielded. So at smaller loads, then the end loads, end fasteners will pick up the highest load. Middle fasteners will pick up the smaller load. But as you keep on loading it further and further and near ultimate, then what will happen? These materials yield. And after once they start yielding, that means the loads become almost like uniform distribution. So in the metal to metal joint, usually at ultimate, the load distribution becomes almost uniform on all the fasteners. So generally when we are analyzing the metal to metal joint, we usually do not bother about this distribution because you are designing for ultimate load and then you are assuming the loads are uniformly distributed on each fastener so you can take the average load. But situation, if you have a composite interface, these two steps are composite, what you will find, because the material doesn't yield, although one could argue, okay, instead of yielding, what happens at when you are approaching the ultimate load, that the damage near the hole will occur, and that will cause similar plasticity effects like what you see in metals. So that means the hole is damaged. So we are not considering essentially for this type of distribution, although at ultimate load, if the fastener holes start getting damaged, naturally the load will try to distribute more uniformly like what happens here. But generally we consider linear behavior, and that means the outer fasteners pick up higher load compared to the middle fasteners. So generally, if the fasteners are of equal size, you may find instead of having 25% load on each fastener, this may be 35, this may be 35, and that means remaining, that is 13, or this may be 30%, 30%, and this may be 20%, 20%. Now again, the distribution of load depends on the type of the fastener, type of the straps, material, their stiffness, and so on. So it could be 35%, it could be 32%, it could be 29%. So it could be varying. And we'll determine using a load shear analysis, which is necessary in the composite joint. Failure modes. What are various failure modes which one can expect in these joints? Can I just ask you the question, have you done this bolted joint in your course at all? Anyone?
Just preliminary.
Okay. Okay, that's okay. So I'll be just talking about whatever is required generally in our aircraft design. Okay, so typical single shear joint. So one of the thing is if the width of the plate compared to the hole diameter is not sufficient, then the failure would occur as a net tension failure. Then there's a shear out. If you have more 0-degree fibers, if there's no very little 45 and 90 fibers, then what you will find that when you are applying the load, it will just pull out as a plug. And depending upon sometimes you may have the cleavage tension failure when you're applying the load. So you may have a failure on this and then failure. So this is called cleavage tension failure. Then bearing failure, where the fastener just bears out on the hole and creates a failure. Out of all the failure modes, what is desirable when we are designing? We want to design the structure that avoid this, avoid this, avoid this, and should be designed with this bearing failure. This is the least risky to design, because in these cases you will find that they all, fell significantly, very catastrophically. But in this case, it is slow, because what will happen, the hole will bear out. It's not going to crash the aircraft. Okay. Other failure mode like bolt bending, and these failures are quite often observed in bolted joints if the straps are thicker, when we'll talk about it. And then bolt pull through the laminate, because what is happening when you are trying to pull this is, so there'll be a tension load in the fastener, and due to that tension, the fastener may try to pull out. A fastener pull through, if you apply a tension load, and then fastener may try to pull, the hole may get damaged or cracks near the circumference of the fastener, and then this bolt pull through may occur. Okay, now, so as I said, there are many modes of failures. So most desirable is when you're designing the joint, aim for bearing failure. And that means the failure load for each of other modes should be higher than this one. Okay, here I've taken some pictures from the same Air Force, that is Delta glass work done just to illustrate various failure modes. See net tension, and you can see the laminate has failed. Here, cleavage. We are talking about cleavage, where you find, the fracture occurring on this plane, and then normal to the load direction. Tension cleavage failure, similar to this. Shear out, where what is happening when the load is applied, you find this, the sort of a plug is coming out. So this is a shear out failure. And this is a bearing shear out, where bearing and along with because this is a bearing, and whole of this plug is then being pulled out. Shear out tension cleavage failure, similar to cleavage. So it's a mixed shearing, tension, cleavage. Okay, now fastener failure modes. There are various fastener failure modes which are possible. Fastener head dished. So dishing may occur, because what happens when you're trying to pull, this will have the load applied like this, so this will try to dish out. Fastener flange shear. Quite often we have observed lots of failure like this one during our tests on various type fasteners. Fastener head shear failure. We have also observed in some fastener the failures like this. Blind or foam head shear failures. So depending upon the type of fastener, you may have a different. Now fastener blind deformed, the head gets deformed. Collar failure, we have seen several times the collar failure or the nut failure. Fastener collar is stripped, this failure. So it depends upon the type of the joint you have. So any of these failure modes can occur. And you want to avoid it. The objective of the design is not to fail the fastener. That should be the last. Fastener shank tension, So we have observed this failure also in some of the joints as this one, shank shear tension could happen, this one, shear tension failure threads, fastener shank failure, fastener sleeve on stamps, different failure. So now, so any of these failures can occur depending on the situation, whether it's depending on type of fastener, diameter of fastener, strap thicknesses, and the loads. So we cannot say when will which failure mode will occur. Okay, here I have listed what I say. Okay, so bearing failure, suppose you are designing P bearing, laminate tension failure, P laminate tension, shear out, all these failure loads for various modes. When you are estimating the loads for failure, because you have to consider each of these failure mode and determine what is possible failure load. And then you design, okay, lowest failure load for safe design. So out of this, we must have PBRG. This load should be the smallest compared to any of these. The reason being, when I said this is the desirable feature, that is a desirable failure mode compared to any of these. You don't want bolts to fail in bending or tension, shear, or laminate to fail and shear out, tension. But so this is what your objective should be. It doesn't mean you are designing for this failure to occur below ultimate load. No, you got to show the positive margin at ultimate load carrying capability. So margin should be positive, but it should not be lower than any other failure mode. That is what objective is. Okay, now I'll show you some data from that report written by S.P. Garbo and Jim Agonosky, Boeing people earlier. They're all retired now. And this work was done by, as I said, by McGraw Douglas before Boeing took it over. And this is published as data. I have sent this report, but it's available free from download from internet. But anyway, I have sent this report. There are 3 volumes and they are very useful. Okay, now, so this chart which I'm showing, what happens, one of the things in joint performance is the clamp up, joint clamp up. When we are designing a joint, you install the fasteners, which we call pre-clamp up. They're torqued. So you are providing some tension load on the fastener, pre-tension virtually, you can call. The idea is to clamp the joint so that you increase the failure load. So what you see in this chart, this is for some joint like 50, 40, 50%, 0, 40%, 45, 10%, 90, laminate. And it's a double shear joint, pure bearing, failure. And as you can see, based on the torque value, say, when the torque is 0, like a finger tight only, there is no clamp up. You have 120 KSI reliable as bearing. Now, bearing is defined as the load divided by thickness divided by the diameter. P by dt is called the bearing stress. So, and as you can see here, as we increase the torque, and this is fully torqued here, and the value is 160 KSI almost. So you can see from 120 to 160 KSI, that means increase of 40 KSI, which is over 30%. So you can understand now the importance of joint clamp up to increase the bearing stress allowable or joint capability. It's very important. When we are designing the structures, I think 2 weeks back somebody asked a question about the relaxation phenomena, and I'll discuss that in this. So, but what happens? Suppose the test is showing the 100% at 100% torque, 160 KSI. But generally, what happens when we are doing the static test of the coupons? We would be applying half the torque, like 40 KSI, say 40 pounds inch, which will provide us the lower value. And this is the value which we'll use in design. The purpose of using the lower value is because we know the joints, composite joints, do relax because they are the viscoelastic materials. They relax with time. So the torque in 10 years of service of the aircraft may come down by 50% or 40%. So in order to account for that, joint clamp up relaxation, the philosophy is to design the joint with the test data considered for the bearing stress allowable at around 50% of the clamp up. Effective edge distance to the joint distance. So this is edge distance. So this is E by D. What you see here, when edge distance is increasing, that means joint performance improves. Suppose you have a 2, again it's 120 KSI, but around 3, beyond 3, there's not much benefit. So around 3, say this is 150 KSI, 140 KSI, so there's significant improvement. So E by D, we designed the structure with having certain E by D value in order to increase the joint allowable. So increase the joint edge distance, increase the joint strength. Shorter edge distance leads to shear or failure. The highest distance is achieved with E by D greater than 3.5. Then the effective environment and W by D on joint strength. Similar to what we considered the E by D, now W by D we consider the width to diameter ratio. So we consider during our design the baseline data, which may be W by D as 5 or 6. So what you see from here, say, when you are increasing W by D, at lower W by D is a net tension failure. And when you increase the W by D, it causes a bearing failure. But what you see from here, increasing W by D beyond 5 really doesn't give you much of a benefit. So generally, design might consider for the joints W by D of 5. The reason being you don't want to consider large value. That means you are increasing the weight of the structure. So you want to optimize. As you know, there's no significant gain by increasing the W by D further. Then, yeah, this is also W by D. effect, net tension failure, and shear out failure. This is T equal to 2 point, I think. Yeah, they are similar data basically, so I won't discuss much about this. Then fastener diameter. Increase in the fastener diameter leads to the reduction in the bearing strength allowable. So there's a diameter effect which we have to consider during our design of the bolted joint. Then CSK by T. This was the question asked over 2 or 3 weeks back by somebody, the countersink to thickness ratio. However, what you find from this result, there is no significant effect of countersink depth to thickness ratio. Here you find this data 0.26, 0.38, 0.77. So there's not much effect. But however, what is happening here, this is a double shear joint. Now, single shear joint, our experience is if you use excessive countersink, then there is a significant reduction. Of course, you're finding here if the laminate is thinner, always the countersink to thickness ratio will be smaller. And so you have a lower value here. So it does show effect, but not so much as single shear joint will show. And that is why there's a limit put, which I put in last time in my presentation. Generally, you aim to design the joint so that the thickness of the laminate is about 50% more than the countersink depth. And that I'll show you another diagram later on. Then percentage of 45 plies. This is very important. When we are deciding about the layups for the design of the joints, then generally around 40 to 50% 45s and around 30 to 40% 0 degree and around 10 to 12% 90 degrees. That gives a good layup. And as you can see here, if you have very high 0 degrees and low percentage of 45s, these numbers represent actually percentage 0, percentage 45, and percentage 90. Does anybody understand, or shall I explain what does this mean? Percentage of number of plies. You see, when we are representing the layup has 4 directions generally: 0, 90, 45, minus 45 to the load direction. So when we say percentage 0 degrees, that means suppose you have a 10 ply layup, out of which 2 plies are 0, 4 plies are 45, and say 4 plies are 90. So that means percentage wise 2 by 10, so 20% zeros, 40% 90, and 40% 45s. That is how we consider. So in this case, suppose it had 10 plies, that means 70. 7 plies will be 0, 2 plies will be 45s, and 1 ply 90. Here you will have 5 plies zeros, 4 plies of 90, and 4 plies of 45s and 1 ply of 90. So what we are trying to say, if you have too many zeros, on one hand, of course, 0 degree is good for the load carrying capability. However, the bearing performance deteriorates because that leads to the shear out failure. And what you see from here, so that means there has to be some balance. Reduce the number of zeros, increase 45s, and that improves the performance significantly, as you can see. And if you improve further the number of plies as 45, then your strength slightly increase further. But between this one and this one, there's not much improvement. So what it says, and I'll show you one of the diagrams where we are trying to show the various important layups which you need to consider for the joints. There would be around 40 to 60%, 45s for a good joint design. Effect-wise distance and layup, bunching of 0-degree plies in single shear and double shear. So this is single shear joint where E by D effect is shown on bearing strength and the double shear. So as E by D improves, we had shown earlier, so this is similar. However, the layups are changing here. The layup one, this is one layup, this is another layup. Again, depending upon the layup, you will have different distance. In fact, this phenomena which I am considering is the effect of sequencing, I'll show better in next chart, which is better to show than this one. Now this one, what this is showing here, this is double shear joint, but one laminate type where you have a fixed percentage of 0, 45, and 90. I didn't write the percentage zeros here. Sorry, total number of plies to be the same. And number of 0-degree plies, 45s, they are same in every layup. So what I'm saying here, suppose this is a layup we pick up 0, 0, 0, 0, 0, 1, 2, 3, 4, 5. Okay, now they are all staggered. Here, you see 0, 0, 0, so 5 zeros. So what we have done, the number of zeros are same in every layup. Number of 45s are same in every layup. And number of 90s are same in every layup. You will find 5 zeros here, 5 zeros here, 0, 0, 0, 0, 0. So that means 5, 5. Now, you have the same number of zeros, same number of 45s, and same number of 90s in total. But in each layup, the bearing strength is different. The effect is due to bunching of the plies together. Now, this is a phenomena which, of course, unless I could talk about the interlaminar stresses, it is difficult to understand. What I'm trying to say, and this is the usual thing in composite joints when we are designing, and when we are designing, whether it's a joint or the laminate analysis when we are doing, that the layups we have to consider that we do not try to bunch up the plies of the same layup or same orientation together. Like suppose you can see here, layup 9, where all the 0-degree plies are bunched together. Here also, they're all together, 7, and 7 is the worst. Compared to A1, A1 is the best where you're having a staggered ply, 0, 0, 0, 0, all staggered. It has the lowest interlaminar shear stresses. This will have the highest interlaminar shear stress, which will cause the delamination failure of the laminate, and as a result, it will reduce the joint strength. So the purpose of showing this one is when we are designing the layups, sequence of layups is very important. Sequence of plies. Any question on this? Is it too much for you people to digest? Hello?
Sir, this is sir, I had a doubt regarding the initial one where you told like the bearing load should be the minimum. If at all failure happens, that should fail first. So is it because of the detectability aspects or anything?
No, it's safety, the joint, because what happens, as you can see from the modes, the bearing, if the hole is bearing, okay, it has the least risk. If you see shear failure, the joint will just pull out. You can see the bolt failure. You don't want the bolt failure to occur. You saw net tension failure, where the laminate will be split into two parts. So that is the reason you do not want a catastrophic failure of the joint, whereas the bearing failure, when it is very slow, it doesn't cause the detrimental effect on the joint.
Okay, sir.
So
Basically, both the parts will be kept together.
yeah,
Even
both parts will be together if it's a bearing joint, bearing
oh,
failure. But if
okay.
you see, if there is a tension failure, which I showed, this one, what will happen? This will just pull out. If this failure, this will just pull out. This failure, it just pull out. Joint will get separated. But in this, you can see nothing is happening. It's just bearing our surface. The hole will get elongated.
Okay, sir. Okay, fine, fine.
Yeah. The worst is this one. You don't want bolt to fail. And quite often what will happen, if you have a thick joint, which I'll consider, of course, the strap thicknesses, bolt failure will occur, like this one, in the fatigue, which becomes critical. So bolt bending, they do design the joints.
Okay, sir. Okay.
Okay, so that is the reason. As from practical, you see here what is happening, how the laminates get separated, where this is plug bearing a shear. I don't have a clear picture where only the bearing, which is just, I'll see, just a hole get deformed. That's it in bearing failure.
Okay, sir. Okay.
That's the reason. Now, my question was regarding this one. Now, the thing is, I do expect that, of course, it's a bit too much to expect. You may not have done interlaminar stresses and effect or layup sequence. It's a bit higher to discuss. But the purpose of this one is to demonstrate when you're designing the layup sequence is very important. You may have same number of 0-degree plies, same number of 45s, and same 90. But the way you arrange them in the laminate is very important. This is what I'm trying to say. So the message is never club or bunch the plies of the same orientation together, which means like this you are seeing in A9, A7, bunching of all the plies together, like 0 degrees all bunched together. So this is the lowest strength compared to when the plies of zeros are staggered. So this is highest strength, it has the lowest, almost 50% strength. I had observed myself this phenomena when I was working in NASA. I designed a coupon and where I did not worry about layup sequencing properly, and I found when I loaded the laminate from the fastener just pulled out like a plug, like a shear out failure. So it's important to consider the joint design properly, the layups. It's very important. Okay, so I just wrote in summary, increased grouping of 0-degree plies decrease the bearing strength, increased grouping of 0-degree plies increase interlaminar shear stress between each group of 0-degree plies and 45 plies, and the increased ILS, interlaminar shear, leads to delamination and thus reduction in bearing strength. So what happens with these layup sequences? They do affect the free edge stresses, which would be taught to you if you are attending some laminate design courses to explain what is interlaminar stress. In fact, that's my one of my favorite topics. If there's a time later on, I might discuss the laminate design and guidance from the interlaminar stress point of view. Okay, now interface fit on bearing strength. Somebody asked last time, sometimes can we use the interface fit fasteners? In composites, generally, we do not use the interface fit. I've got some data from that same Air Force lab report or Merrill Douglas work. What you see, there are two types of layups here. And nominal fit, which is generally the clearance fit. Then 3000 interface fit, we call 0.003 inch, and this is 0.008 inch interface. That means the diameter of the hole is smaller than the fastener diameter by 0.003 inches. And here 0.002, so 8, and similarly here. So you see, that becomes the interface fit. At RTA, the strength which you see, what you are seeing here, there's no improvement in the static bearing strength reliable due to the interface fit. For hot bed, of course, this is showing slight improvement. Same thing here, and nominal 0.2 and minus 0.46. So again, and in fact, what you see here for this one is decreasing. So essentially, the message from this one is the interface fit doesn't provide any benefit in the composite. On the contrary, the downside of this interface fit is if you try to put the interface fit fastener, pushing the fastener into the hole, during that process, you may damage the hole and reduce the strength. So, general practice in composite says not having the interface fit. Usually they are class 1 holes. Class 1 hole is when the clearance between the hole and the fastener is 0.001 to 0.003 inches. That's a clearance, not interface. So hole is slightly larger than the fastener, so that fastener can easily be pushed through the hole. So remember at least that don't have interface fits ever in composite structures. Metals, they are done, but not in composites. In fact, even metals, we use clearance fit. Like fittings, you don't have the interface fit fasteners. the all clearance. Same. 1, 2, 3 thou clearance. So intervention fit shows insignificant effect on bearing strength. However, intervention fit may damage the hull during installation. In composite, intervention fit is not recommended. Okay, effect of porosity. So when you are making the laminates, there is a possibility some laminate might have a porosity. And porosity does lead to reduction in the strength of the laminate bearing strength. So you see there are percentage changes. Moderate porosity, I can't give the number, whether it's a 2% is nominal is 2%, this is 4% or 3%, and severe porosity, it might be around 7 to 8%, I believe, but the number is not there in this report, so I can't quote that. And you can see as the porosity is increasing, the bearing strength is reduced. Okay, now the bolt clamp up relaxation in composites. Effect of the clamp up. And we talked about it that composites are viscoelastic materials. As a result, during surveys with the time, because initial clamp up force is there, and when it relaxes, that means it will be relieving the clamp up force. So with time, qualitatively, say the clamp up force will come down. So as a result of viscoelastic material, clamp up force will relax with time and environmental effects. I've just written down some parameters which may affect your relaxation with time. Joint strap material properties depends upon the type of laminate, layups, materials, because that will affect the viscoelastic relaxation phenomena. Number of types of joint straps, whether 3 straps, 4 straps, or 2 straps. Strap thicknesses, sealants, you might have sealant at the joint, shims, fastener and collars type, material, sizes, pre-torque of joint stack to diameter ratio, temperature, moisture, and so many parameters which will affect the relaxation. So it's very difficult to pinpoint, okay, whether it's going to 50%, 40%, or 20%. Just some calculation I picked up from one of the reports done by Shiv Kumar and Cruz. And what you see, a joint and the clamp up force. F, which is the clamp up force, is equal to T by KD. T is the torque. K is frictional coefficient, normally varying between 0.1 and 0.2, and D is the fastener. A relationship for the bolted joint clamp up force relaxation is given by Ft. F naught is some parameter, 1 plus K nu, and so don't worry about this. And the equation. F naught initial clamp up, T time, clamp up force, viscoelastic clamp up constant, shift factor. So don't worry about this, I won't worry. Now, the result is, based on analysis, as you can see for some joint, and of course it will depend upon the thickness of the straps. But what Shiv Kumar found, that with time, the relaxation, and this is a test data, and this is analyzed data, analysis, and this is a test. So you can see, say in 1,000 hours, the relaxation in the clamp up occurs by about 20%. It's a logarithmic chart, and so you can see initially the relaxation will be more, and later on the rate of relaxation will reduce. So just a description which I have described anyway. Shims and sealant, the use of various shims and the sealants, because shims are required to achieve the fit up when the two parts are joined together. Suppose the spar and the skins, when they are joined, you may find the spar and skin. They may not be fitting well. There may be some gaps. And so you need to provide some shims in order to fit. And suppose it's a metal, aluminum. You might put some sealant in order to provide the joint protection. So shims and sealant, they are used in joints, but they are not helping in terms of the structural integrity of the joint. They always play an evil's role. I consider shims and sealant to be evil in the joint, necessary evil. Shims, so you may have different types of shims, solid shims. Shim material could be titanium, stainless steel, pre-cured composite laminate, preferred for critical highly jointed. So solid shim, when we are saying like metallic shim, it could be titanium or steel or laminate. They are preferable if you have a critical joint design. For the critical joints, like primary structures, fittings, you may like to have the solid shims. Then there are P-level shims, laminated P-level shims like titanium, laminated stainless steel, laminated Kapton film, polyamides, and their performance is poor compared to the solid shims. In critical joints, usually I would not recommend these to be used, only these. Moldable shim, there's a liquid shim, which is some kind of PR compounds, elastomer materials, used for filling mismatches between the metallic or composite parts. Use of such shims may degrade the joint performance due to loss of joint clamp up. They are also not used if the joints are very critical in those areas. But sometimes they may have to be used because for the corrosion prevention. Effect of shims on joint performance: increase of joint stack thickness leading to increased board bending, relaxation of joint clamp up, fastener collar rotation, reduced static strength, reduced joint stiffness, and reduced fatigue strength. As I said, shims are necessary evil sometimes. They don't help, they only degrade the joint. As you can see from here, effect of shim on static bearing strength. You have a solid shim and you have a liquid shim. Liquid shim, when we are saying, I said, elastomeric materials, moldable, and you can see the degradation. Suppose shim thickness is only 0.5 millimeter, and 0.5 millimeter thin ship will bring down the bearing strength by 10%. However, what happens here, this data seems to be on the roof for the room temperature, but if you are designing for hot wet conditions, these curves will pull down further, so you will have significant degradation in the joint strength for the hot wet condition. So as I'd been discussing, the shims are necessary evil, but got to live with it. Apply the correction factors appropriately for the joint design. Sealant. Joint sealant have similar effect on the joint performance as a liquid shim. Avoid the use of sealant in critical joints. Fastener materials. There are various types of fasteners available. Generally, in composite structures, we use titanium alloy fasteners. Internal we would use only if we are not able to meet the joint strength requirement using a titanium fastener. The reason being, internal fasteners are far expensive compared to titanium fasteners. But of course, they have very high strength compared to titanium, and sometimes there could be joints which can't be designed using a titanium fasteners to carry the amount of load which you want. So go for internal. We had to use at many places in the structure the internal fasteners when we could not satisfy our load carrying capability using titanium fasteners. Especially in the fatigue, internal fasteners are much better than titanium fasteners. Then you have corrosion resistant steel crests. They're also good fasteners. They are used quite often. Then another corrosion stainless steel is 826, 286. So all these materials generally are used in composite joints. Fastener compatible with carbon epoxy composites. I have not listed other fasteners which may be used in aluminum structures more often, but relevant to carbon, even aluminum structures you may find similar fasteners to be used. I don't know about it. Effect of parameters on bearing strength for joints. Various parameters which affect the joint strength are joint configuration, joint steps materials, laminate material and layup sequence, strap thickness, weight, bolt and collar types, material diameter, joint clamp up, edge distance, loading type and magnitude, temperature, humidity, shims, sealant, hole grade. Let me tell you one thing. When we are trying to develop the alliables for the joints, we would consider each of these parameters independently and determine the effect of these parameters on the joint strength. And then we apply the correction factor. Suppose we have baseline which we have designed for a particular nominal W by D, E by D, the thickness, the layup sequence, and top, the hole size type of the fastener. Then if we are working with another fastener type, another hole type, we will develop the correction factors for those parameters applied to the basic design value. And that is how we would cover the effect of each parameter in order to determine the strength of the particular joint having those parameters in use. So when we are doing the testing, the heaps of coupons need to be tested. As you can imagine that when you're varying these parameters, you got to test tens and tens, they run into hundreds, several hundred coupons for the joints. And then you will have some element test, you will have some subcomponent test in order to validate the performance of the joints in static and fatigue. It absorbs a significant amount of testing time to validate the joints. As I've been emphasizing, joints are the most important design components of this structure. So a lot of efforts should be spent, in fact, to validate the joint. You don't want in service the joints to fail. CSK, this is the same slide which I put in the questions and answers to show to avoid knife edging T1, that the thickness of the strap should be greater than 1.5 H or H by T less than 0.67. H is compressing depth. Okay. Now, the layups, type of the layups, which normally you like to consider for your joint designs are, say, percentage 45s and percentage zeros. The prefabricated joint design is around this space. So that means 45% should be between around 40 to 80%, 60%. I think it's shown a bit higher. I wouldn't go that high. I mean, maximum I would go around 70% or less than that. And zeros between this and this, which is around 15% to 35%. But optimum joint design, I usually call somewhere 25, 50, 25. Okay, now this is showing the data for the bearing stress contours for graphite epoxy laminates, which I have taken from John Artsmith's paper. What is showing percentage 0° plies, percentage 45s, and it's showing these stresses, bearing stress contours, 130, seems to be, I think these have slipped, 130, 140, this should be this should be 130 here, and say 145, 145. So depending upon that, you can see here, and so that means you are achieving highest bearing strength allowable somewhere here, which is lying again between 40 and 60%, somewhere around 50%, and zero around 25%. So that gives you higher bearing strength allowable in this range where 45 is around 50% or 40 to 60%, and zero between 20 and 40%, around 25%. So this gives you the best layer. 25, 40, 40 to 60, and 10 to 12% for 90 plies. Okay. Now, does anybody have question or any suggestion on this? Is it too much? Because now, I might just close today here and continue with these parameters to discuss the effects tomorrow. Now, any questions so far, and all the things which you would like me to explain more? Any questions, please?
Sir, generally, are these clamp forces, means the bolt is loaded to its yield or anything?
I didn't understand
Clamp up forces, how they are determined?
how the joints forces are determined.
I mean, the pretension given to the bolts.
Oh, pretension. Generally, what happens? The pretensions are the function of the bolt diameter and the material. So
Are they loaded to the yield point or anything, or close to yield?
yeah, near yield normally they are, and they are decided. But the thing is, in composites, the pretension is different in composite to composite joints than the metal to metal. Because what happens, you can't put too much of a pretension in composite to composite joints also, because you might crush the laminate. So there's a limit. And there are specifications to allow the clamp up. It is with the fastener data, saying Boeing or aerospace fasteners data will show for a particular type of fastener what is the maximum clamp up one should use, or torque value, pre-torque. For the composite, so composite joints will be different, metal joints will be different, the pre-torque value. So that depends on the collar or the nut and the fastener type, material, diameter. So these are specified essentially, which has been developed based on the test data by the companies. Calculations and test both. So I might just try to, if I can find some characteristic values, I might show next time the pretension value normally.
Okay, sir. Thank you.
So these are normally specifications. In fact, companies do develop, like say Boeing. We had for each fastener, each collar diameter, we had the booklet, which will give you a top, and that's what you put in the drawing. And that's compulsory, that's specified, and characteristics you use it. And when I was working with the Airbus project on landing gear, the same thing. They also had provided the tables of fastener torque up, clamp up. So the industry uses the clamp up values. They have determined it based on certain tests and calculations. Okay.
Professor,
Okay,
I have.
Yeah. Yeah. Your sound is breaking. Can you? Hello?
Am I audible now?
Yeah. Carry on.
Yeah. I wanted to know more about the prevalence of welded composite joints when it comes to thermoplastics, or are they prevalent in aircraft structural designs?
Good question. Thermoplastic welding, you are saying, right?
Yeah.
Now, there was a lot of work done here actually for thermoplastic welding at CRC. Almost, I can tell you, go back to 30 years. And, but I've not seen the success for that. That's not being used currently. At least I don't have any knowledge that we have used anywhere the thermoplastic welding. I would not rely on it. So are you working on thermoplastic welding, or?
I was just curious because only when it came to mentioning fasten joints, only bolted as well as adhesive were addressed.
Yeah.
So I thought, this is also.
No, it's a good question. I deleted myself from my presentation, even though I know Michael knew his book gives third one, but I considered that to be just for the information's sake. So I didn't want to emphasize on that because that is not being used. I know about it. It was being developed here in Melbourne by Cooperative Research Center. And I know they were doing a lot of work on it, but it has not found success, at least. I wouldn't rely on it. And that's the reason, you know. And that's why I'm not,
Thank you, Professor.
I've not even considered in my presentation that mentioning of that. Sure. But good question. Any other question? Now, I just want to ask you, are you finding this useful or is beyond the scope of your, the course? Or you want me to cover something else?
Sir, what is the bolt material, sir? In this, we are using this laminate, composite laminate. But
Yes.
bolt,
Yes.
is that metal, sir?
Bolt material, as I said, normally in composite joints, quite prevalent material is a titanium. Titanium alloy fasteners are the most common which are used in composite structures. Then, as I said, in some cases, what is happening, titanium has a lower strength compared to Inconel. So in critically loaded structures, when we could not meet the requirements for the load carrying capability using titanium fastener, then we went to Inconel. Inconel has much higher strength reliable compared to titanium fastener. They are pretty good fastener. Unfortunately, they are too expensive. So it's a cost performance benefit one has to see. If you can't meet the requirement using titanium, then you have to go for it Inconel, irrespective of the cost. Then another is Crash. Crash, these fasteners have a better strength reliable than titanium. A286 and this one. A286 is quite common. And so it all depends upon the joint loads, and then you decide about the materials. But these are the three materials which are used for joint. That's it. There's no fourth material in the composite joint. Titanium, Inconel, and Crash. Corrosion resistant steel. You don't use aluminum fasteners. No.
Is it possible to use aluminum, sir? Aluminum 202?
No, I would never use them. One of the things with aluminum is, of course, aluminum has a very low strength, not very good for fasteners. Another thing is aluminum to carbon corrosion, galvanic corrosion. You won't touch aluminum into the aluminum as aluminum as a fastener in composite carbon.
But in metal, sir, we can use aluminum.
Metal, not the fastener. You don't use the aluminum bolts, usually the rivets.
Rivets.
Yeah. But not bolts. Bolts are usually either steel, titanium, Crash.
Correct, sir. Okay, sir. Thank you.
Any other question? Any questions? for anybody?
Sir,
Yeah.
One more question, sir.
Sure. Carry
Sir,
on.
to find the strength of the joint for different stacking sequence, so you have to plot the graph strength versus different stacking sequence and then find, or any other direct method is available, sir.
Okay, now stacking sequence. Okay, let me show you the chart over there. Generally, what will happen, we might test a couple of laminates having a different stacking sequences. Generally, what happens, we know that which is going to the worst layup and which is going to be the better layup. The recommendation which we have is to distribute the 0-degree plies in the laminate. And our guidance, normally we put that never have more than 3 plies of zeros together, almost. I normally tell if you can avoid putting even 3 plies together of zeros together, 2 plies only. But sometimes what happens, you have a large number of 0-degree plies, and if you try to stagger 0-degree plies between 45s or 90s, you may not have much choice because you need more 0 degrees. So sometimes it becomes necessary to club 2 plies or 3 plies together, but minimize the clubbing of plies together. Because clubbing of the plies or bunching of the plies of the same layup increase the interlaminar stresses, which degrades the joint and the laminate performance because it creates interlaminar stresses. And you determine the strength by using the test data of a couple of layups to see the effect. Was that the question?
Yes, sir.
Okay.
But sir,
Yeah.
right, you have mentioned 40/50/10 layups equal to 0.208 inch.
No, that's a thickness. This is thickness of like this is percentage. 40% zeros, 50% 45s, 10%. That is how we represent.
Okay.
So what you see here, the percentage of zeros is 40%. As you can see, number of
okay.
So number of 0-degree plies in each layup is same. The difference between each one is how you distribute the 0-degree plies. You can see here, 0-degree ply staggered. Here you have 45 together, 90, and then zeros together. So look at this, A1 to A7. A7, the lowest, A1 is the highest. So the rule is spread the 0-degree plies, not bunch them together. Now, this takes some time. I would have shown the effect. How does it work? The stacking effect on the interlaminar stresses.
Yes, sir.
Mm-hmm. So, but maybe next time I might show you 1 or 2 slides to make you clear what do we mean by interlaminar stresses, which doesn't exist in metal. So this is a typical phenomena here in composite, the interlaminar stresses at the free edges, which cause the delamination failure. Okay, any other question?
Yes, sir. So this is Ajit.
Yes.
So any specific reasons for not using interference fit in composites?
Yes. There are a couple of reasons. First thing is it does not improve the performance. I showed in the slide, the interference fit does not give you any benefit. Second thing is, while you have the, fastener is larger in interference fit, fastener is larger than the hole. When you are installing the fastener, you have to put the fastener into cold environment and then install the fastener. Otherwise, you can't fit it. You have to shrink it. Now, in that process, you might damage the hole. Another thing is, imagine a situation if the 1,000 fasteners to be put in an assembly line, and if you want to make the interference fit, it's going to take enormous time to put the fasteners. And these days, the things are done by robotics, robotic drilling, installation of fasteners. There's no way you can do the installation with this interference fit. It's a waste of time. It only can degrade the joint, then improve it, because interference fit during the installation in the composite may damage the hole. Also in the metal, then when the holes are being drilled and they stack, you have a fitting carbon all together. The drill is drilling the hole. It is going through metal, carbon together, say. Hole is of the same size. The fastener is same. There is no interference fit. So whether it's a metal or composite, we don't use interference fit.
Okay, sir.
Okay, so that's not a current practice of interference fit for these assemblies.
Okay. So it's not specific about composite. It could be metal also. We cannot use the interference fit.
Well, yes, generally, we don't use it. The bolts, because what happens, the bolts when you're using, they need to be replaceable in metal fittings also. If you have an interference fit, you may not be able to replace it. It's a nightmare. So interference fit wouldn't even bother about it. We don't consider interference fit at all. At least in my career, I have not seen any interference fit fastener being used on the assembly. Metal or composite, any structure. So, any other question?
Then, sir, what kind of fit it is? Just normal push fit. There is no tolerance.
No, I think your question is not clear.
I mean, interference fit. If it is not interference fit, there is that means what would be the tolerance? Okay, between the hole and this bolt diameter, sir.
Generally, is 1:3 thou. Thou means 1,000th of an inch, 0.001 inch to 0.003 inch.
Okay.
So that's a standard fit, what we call class 1 hole. You don't want the hole to be larger because then it will degrade the joint significantly. So the standard is 1 to 3 thou clearance. That's it. So the hole which is being drilled would have the minimum dia will be diameter of the fastener plus 0.001 inch, or in terms of millimeter, it will be 0.025 millimeters to 0.075 millimeters clearance. That's it.
Okay. Okay, sir. Thank you.
Yeah. Any other question? Okay, if there are no questions, then I can close this, and we see you tomorrow. So we'll have the next lecture tomorrow.
Sure, Dr. Garg. Thank you.
Okay.
Tomorrow
Thank you
around
for-
same time, sir.
So, Professor Dinesh, do you find that this material on the bolted joints is useful to them? And
Most definitely, Dr. Garg. So though not all of them might be directly working on it, it's something that is of tremendous significance for them, whatever they eventually do. Because if they're working on composites or any structures for that matter, they have to sometime or the other face joints.
yeah, that's right. So this is applicable to aluminum joints also.
Absolutely, yeah.
So I'll be talking about the modes of failure and some determination of the strength and analysis. So that will be useful to them for any joints. Okay.
Sure.
Okay.
Yeah. Thank you very much.
Good night. See you tomorrow.
Thank you, sir.
Take care.
Okay, bye.
Thank you.
Thank you, sir.
Thank you, sir.